Okay, so in this chapter, what we are first going to be looking at is where we have come so far and what we are going to be learning in the future. All right, and the one thing I always tell all the students who do this module is when you eventually complete the module and you learn about RTOS and you realize that it's a very powerful tool, it is something that can really help you. Don't jump to the assumption that you should now use RTOS for all your projects. Okay, so RTOS is like a very powerful sort of a tool that you have. Okay, you don't necessarily need to use that tool all the time. All right, it's just like if I give you a piece of wood to saw in half, you can just take a normal saw and still do it. You don't need to buy a high powered chainsaw to come and cut a small piece of wood. All right, so the idea is you have a task, you have an objective. Okay, in some cases, what you have been doing so far may be more than enough to solve the problem. Okay, so RTOS is useful, okay, but you must also think about whether it is really needed in the situation. Okay, so let's get started here. So in the last lecture, we also had a bit of the concurrency concept. So we talked about concurrency, right? Then we had this review of the various peripherals that we have in our system already, right? So from the microcontrollers that they've used in the past, you already know of like timer peripherals, A to D, D to A, serial interface, correct? You know about memory interface and so on, GPIOs. Okay, so you already have been exposed to the concept of the peripheral blocks providing a level of concurrency, right, through the concept of interrupts. So by using interrupts, we are able to capture events as and when they occur, right, whether it is triggered by internal events or external events, and we can immediately get the attention of the CPU to do something useful for us. Okay, so this concept of concurrency has already been there, okay, and we know sort of how to apply it, all right, from our earlier modules. All right, so this is the example we saw from the last slides. So we have a timer peripheral. So the timer peripheral will basically keep track of a periodic interval. Okay, so the idea is every time it will trigger an interrupt after a certain amount of elapsed time. Okay, and then when the timer interrupt eventually occurs, okay, it will start the ADC. Okay, and when the ADC is done, the ADC generates an interrupt that tells you the ADC operation has been done. Okay, and in this case, you trigger it 4 times, all right, and then you capture the values. Okay, and once you capture the values, okay, in the ISR, then you set a flag. Okay, you set a flag so that the main program, so this is your main program over here. So your main program will be probably checking for this flag to know whether this operation has been complete. Okay, and then it does the next one and so on. Okay, so this level of concurrency, that means parallel processing, is already there with the help of hardware. Okay, so in this case, like I said, for simple systems, it is more than enough. All right, so it always depends on how complex a system is. Okay, because the interrupt system is good, it is very effective to capture the attention of the processor. So when you have basic processing that you need to do, like whenever I press a button, like if you take your TV remote or your aircon remote, okay, when there's no button press, I can go to a sleep mode. But the moment there is a button press, I will want some immediate attention to process, to understand the button and generate the appropriate wireless signal. Okay, so in a simple system, this interrupt-based approach works very well for us. Okay, but when you have more complex systems and your requirements become more particular about time, then we want to increase that level of performance from the processor as well. So how can we make the processor more responsive? Okay, so in the hardware sense, we are limited, right? Because when you choose a microcontroller, you are already limited by how many timer modules it has, how many GPI interrupts it has, and so on. So you are already limited in the hardware sense. So the next best option is to look at it from the software perspective. Okay, that means instead of just relying on hardware concurrency, why don't I do it from the software perspective? So we learn to share the processor by splitting up our problem into many small problems, okay, which we call software threads or software tasks. Okay, and that is what we are going to be learning how to do in this module. Okay, so the idea of a task or interrupt is, in a sense, slightly interlinked. Okay, in the loose sense that you are allowing some form of parallel processing. All right, but in the difference between task and interrupt is, if you look at this context over here, all right, when I am busy doing something, so let's say this is my main program here. Okay, and I'm busy doing something, and at this time instance t, there is an interrupt. Okay, so we understand from a processor's architecture perspective. Okay, I talked about it as well. Okay, so you have a fetch, decode, and execute cycle. So whenever you fetch a new instruction from the processor or from the memory, you pass it through the processor, it goes through multiple stages before it finally finishes execution. Okay, so when interrupt occurs, the processor could be in the midst of performing an instruction, so it needs some time, all right, to finish that instruction that is already in the midst of processing. Okay, and once that is done, you also need to do the context saving. So the context saving is what? Because while you are in the midst of executing instruction, you are using the internal registers. You have a value for the stack pointer, for example. Okay, you may have been using some of the other memory regions and so on. So you want to save the context. That means exactly what you were doing, what was the program counter, what were the register values, and so on. And once you have done all that, then you can finally jump to the task or the ISR. So in this case, let's assume it's ISR. So when I'm doing when I'm executing the code for the ISR, nothing else is happening at the software side. All right, that means there's only one code being executed at any point of time. It's either the main program or the interrupt. Okay, once I'm done with the interrupt, okay, when it's complete, okay, then I'm able to restore the context. So this is where you restore. So restore means you are planning to go back to the main program, so you need to reload all the values of the registers, the program counter, and so on, and then finally you go back and continue with your main. Okay, so that is the concept of interrupt, I think, which all of you know. Okay, and that is sort of consistent across all controllers. All right. So though internally the registers involved, the way it may use the stack and all this stuff may be different, but the concept is always the same. All right. So for the hardware side, we are able to do it with interrupts. All right. But for software side, okay, let's look at how we can go about sort of using the CPU more effectively by trying to manage the overall objective into a set of tasks. All right, so this is one thing that we looked at previously, where we just have a simple system like this, where you want to track the bike, sort of your performance of your cycling. So you can have, for example, 3 interrupts, okay, for different inputs, the wheel rotation key plus maybe a clock, okay, real-time clock, and then you have a simple display over here. Okay, so when I look at this system, it is a simple system, no complexity, very low complexity. So I can easily use any 8-bit controller. So you can easily take your Arduino Uno or anything, and you can program this requirements very easily. All right. So this is just a simple sort of a pseudocode to give you the idea. All right, but again, you know all this stuff. All right, writing ISR, you know what to do in the reset and so on. Okay, so in this example, basically, if you look at it, your main program does nothing more than just sleep. So it may do some initial configuration, set some global variables, and after that it just sleeps, and then you just wait for the interrupts to trigger. Okay, so this mode of operation is good for power consumption, because when you are not doing anything, you allow the processor to go to a sleep or low power mode. Okay, so that is why in most of your remote controls and so on, you can see that the battery can last for very long, 1 year, 2 years, and so on. Okay, because when you're not pressing any button, you're not using it, you will go to a sort of sleep mode. You will shut down its LCD display, the backlight, everything. Okay, so that allows you to conserve power, and when you press a button or something happens, then you activate the processor back into mode. Now let's look at a more complex application, okay, where we have a GPS-based pothole alarm and moving map. Okay, so this is more complex. Okay, of course, this kind of potholes you don't see that often in Singapore, because I think Singapore, we do a good job in making sure the roads are all well maintained. All right, so we don't see that many potholes, or even if you see it, usually gets cleared up quite quickly. All right, but again, this could be a problem in other areas. Okay, and when you're driving, you want to avoid potholes. Okay, you can damage your suspension. Okay, you might lose control of the car and so on, especially in high speed. Okay, so this application here is to detect, okay, and sort of alert the user, all right, when it sees or when it knows that there's a pothole nearby. So let's examine what are the different tasks. Okay, so of course, when you are going to develop a system like this, you will have a lot more functions and so on, but at a very abstract level, okay, you can sort of break it down into maybe 5 different sort of tasks. Okay, so the first one is your decode, where you want to get the GPS information, and every time you get a new GPS data, you want to decode it. All right, so you know the current position of the vehicle, and then you need to already have a database, right? Because you need to know exactly where are the potholes, and then you compare, okay, based on your location with the information from the database to know if you are approaching any pothole. Okay, sometimes you want to update the information, right? Because maybe you come across a pothole which is not in the system. All right, then you want to update the system so that other users can now know that, okay, there is now a new pothole found in this particular location. So you can record some new information to memory, all right, and maybe later on when you go back home, you can maybe download that to the server and so on. Okay, and for basic operation, you have some switch, okay, for user inputs, and LCD for updating the map. So again, this is just a very simplistic view, okay, of the software tasks that may be involved if, let's say, you're going to design this system. Okay, so now comes to the important question, right? How do I schedule these tasks? Right, because you know you need to do all these things. All right, but how do I schedule them? All right, so what are the fundamental questions you can ask? Do we have to run the task in the same order every time? Okay, does it have to be in the same order? That means, does it have to be decode first, then check, then record, then switch the LED and LCD and so on? Or if not, can I jumble them around as and when things happen? All right, so the way you divide your overall objective into different tasks may have some implication, right? Whether they have to go in a particular order, or you can actually run them in any particular order as well. Okay, and the other consideration is preemption. Okay, if one task is running, must I ensure that it completes, or can I abandon it halfway to allow somebody else to run? All right, so these are important questions we need to ask ourselves. All right, when we are looking at how we are going to schedule these tasks. So let's look at a very simple one that probably we'll all start off with. All right, so the most simple one, all right, that we want to maybe just test the functionality is you'll put everything in a sequence and run it as a while loop. Okay, so it's a very simple approach, and I would say most of us would probably take this approach as a starting point just to make sure that everything is working. Okay, so we run in a sequence. Okay, we decode, we check, we record, we check the switch, check the LCD, and so on. Okay, Now, of course, this is very simple, okay, but the fact is it does not take into account any changes in the conditions. Okay, and all the tasks run at the same rate. Okay, that means if I say that this whole sequence takes t seconds to complete, okay, then each task will only run one time in the interval of t seconds. Okay, and it means that when I complete one, let's say if I just complete decode, I need to wait for the full t seconds before the next iteration of or the next time I have an opportunity to run the decode one more time. Okay, so the delay is consistent. Okay, it's always I have to wait the same amount of time before I run it the next time and so on. Okay, so this may not be desirable, okay, in some cases. Okay, and we will see why it could be an issue over here. Okay, let's look at this situation here where the GPS data arrives after I finish the decode instruction. Because the objective of the decode instruction is to actually analyze this GPS data and give me a sense of where I am. Correct. But if the time the new data arrives is just after I finish that function, then I have to wait the full cycle before the next time. Correct. So I have to, okay, from here, okay, I need to wait until the full cycle over here, and then I can actually start to look at the new, the new decode is here. Okay, so I need to wait for the new decode to run after I finish the current cycle. And after I finish the check, then I can know whether I'm approaching a pothole or not. Okay, so you have to understand that the way we have designed this system is you decode is to first sort of interpret the data that comes in, and after that you still need to check with the database, and then only I know that whether there's a pothole nearby or not. So if my GPS data comes after I finish the decode and check, that means when I'm starting the record cycle, then I need to wait, okay, until the next decode and the next check, then only I know, okay, whether a pothole is nearby. So this is of course not ideal, correct? Because by the time, okay, if you are driving quite fast, you may have already hit the pothole. Okay, so by the time you can even get a response from the system. So you can see that this static schedule is not ideal, correct, in a situation like this where timing is now critical. Okay, whenever new data comes in, I want to be able to process it and quickly update the user what's happening. So once timing becomes an important factor, okay, the approach that we are used to may not necessarily be the best already. Okay, so the next option is dynamic scheduling. All right, that means instead of going in the same sequence all the time, I can change the schedule. Okay, I can change the schedule based on the option, based on the importance. All right, that means I give some level of priority to different tasks, and then I decide, okay, who is going to run next. Okay, and in this approach of dynamic scheduling, there's also further subdivision. Okay, one is you call it run to completion. Okay, in run to completion means if I have already started a task, okay, but somebody more important comes along, I still run my current task till I complete it first, and then I switch to the more important task. All right. Whereas in the preemptive approach, the moment a task of higher importance comes along, I will immediately switch over. All right. So that is the sort of sub level of this dynamic scheduling. Okay, so let's look at the first one, dynamic run to completion schedule. All right. So in this dynamic run to completion schedule, what happens is the GPS data comes here. Okay, right after or right when the record task starts. Okay, but since the record task has already started, okay, and in our system we say the GPS data is higher priority. That means the decode function is higher priority. Okay, because every time a new GPS data comes in, I need to quickly process it to know where I am. Okay, so the moment the GPS data comes in, regardless of any function that I'm currently running, I will run that task till I complete. Okay, so I'll run it to completion and then the decode task will start. Okay, and then I can do the check, and once the check is complete, I will know whether I'm approaching a pothole. Okay, so this is of course a huge improvement over the previous static cyclic scheduling. Okay, that means I now only delayed by at most the current task that was executing when the GPS data came in. All right. So when you look at this task state, okay, so this task state diagram, you just take it as an idea of how a system may switch between different tasks. Okay, when we are moving to the RTOS part, okay, you will get a better sense of the task state and how they actually, or how a task moves around between the different states while it is in the system. Okay, so in this example, okay, we can say that you have a list of tasks, okay, that are ready. Okay, so in our case, we have the decode, we have the record, okay, we have the switch, we have LED, and so on. Okay, so we have all these tasks, and all of them could be in a ready state, or some of them could be in a ready state. Okay, and the objective of the scheduler, or the aim of the scheduler, is to start the highest priority task that is ready. Okay, now of course in our system maybe we say that decode is the highest priority. Okay, but decode may not necessarily be ready until a new data has been detected by the GPS module. Okay, so if there is no new data, then I can just follow through the sequence. Okay, so if in your system maybe you have programmed it such that GPS data or incoming GPS data may trigger an interrupt, and from there I can set some flag to know that the new data is ready. Okay, so if the decode information, decode task does not need to run now, then I may run the other tasks in a sequence. Okay, but the moment the decode is ready, okay, then I will have to transition that to the running state. Okay, so all the tasks, okay, in this sort of idea here is they are in a waiting state, and the scheduler will select one of them, okay, to go to the from the waiting to the ready, and those tasks that are in the ready state, one of them will go to the run. Okay, so when you say a task in the waiting state, it could be, for example, decode. It is waiting because it is waiting for the new data to arrive. All right, so in a sense, this may be better because I do not need to keep on running decode if it's still the old GPS data. All right, I'm not going to get any new information if I'm still holding on to the old GPS data that was already decoded. Okay, so I can still be in a waiting state. But the moment a new data comes in, I may transition to the ready state. Okay, but when I'm in the ready state, okay, maybe another task was in the running state. Okay, and over here, okay, previously maybe after record was switch and LED. Correct, but the moment the decode transition from waiting to ready, decode went to the front of the queue. This is the top of the queue. Okay, waiting to transition to the run state. So that is how the scheduler works. Okay, it sort of maintains a queue on which task is going to transition next. Okay, so the higher priority task, when it transitions from waiting to ready, it will automatically go to the front of the queue. So when the current task that is currently running transitions out, okay, that means it is already completed and waiting for the next turn to run, then the decode task, which is in the top of the queue, can now transition to the running state. Okay, so that is the sort of the concept of how a scheduler works. Okay, but again, we will revisit this in more detail later on when we go into the RTOS option. Okay, so just now what we saw was the dynamic preemptive dynamic run to completion scheduler. The other more responsive option, I would say, is the dynamic preemptive scheduling. That means regardless of what you are doing, okay, so here the record started, the record function actually started. Okay, but just immediately after that, the new data comes in. Okay, so even though you have already started record, but because the new data comes in and decode is considered to be higher priority, okay, you will automatically transition from the record task to the decode task. So I will immediately switch off. Okay, so the scheduler will immediately switch out the record task and load the decode task to the running state, so that you can, with minimal delay, decode the position and check, okay, for the pothole. So this is what you call preemptive. That means you immediately stop what you're doing and you take over the CPU. So this is very much like how interrupts work. Correct. So interrupt is the same thing. Okay, your main loop can be running something, but the moment the interrupt occurs, you are able to immediately stop and service the interrupt. Okay, so it's the same concept, but now you are managing it all within software. So it's not dependent on hardware. So if you look at the response times, okay, comparison, you can see that static is of course the worst case scenario. That means you run it in the same schedule all the time. All right. In dynamic, if you run the completion, it's of course a lot better. Okay, but the most responsive is of course the preemptive approach. Okay, so these are again the common sort of schedulers, all right, that are available. But we are going to have another more detailed lecture on scheduling policy alone. Okay, later on. Okay, so we will come to that later. Okay, so there's a question: decode and check separate tasks? If so, how to ensure that check actually happens after decode? Okay, so to ensure that, okay, so if you go back to this sequence here, okay, if let's say now, if I come back to here, and I want to make sure that after I run decode, okay, or the moment decode goes to a ready state, I want to do check, correct? So what I should do is I should make sure the check is maybe the second priority. Okay, and the moment decode is activated, okay, that means some flag is set by the incoming data that new information is available. So I sort of transition decode from waiting to ready. Then that same flag can also transition the check function to ready. So when the check function, which was also in the waiting state, will also come here. And since decode is higher priority than check, then the sequence will always follow this way. Okay, so the way in which you order priorities can be a way to do this, but we will learn other techniques as well. Okay, when we are actually dealing with OS later on, all right, we will actually see how one task can synchronize with other tasks. Okay, like the question, how do I ensure that check always comes after decode? So you can have multiple tasks. Okay, so even though in this concept you might think that anytime anything can happen, but at the same time you can still enforce some level of sequence, right? Depending on what you want. That means in this example, decode must always run, then check must be done. Okay, so how do I enforce that? So one way is of course priority. What we will be learning later on is inter-task communication, what we call inter-process communication, IPC, where tasks can talk to each other in a way to ensure that when one task completes some level of activity, then another task can take over after that. Okay, so these are things we will be learning later on as well. Okay, so this is an example of the typical way in which we will do it, where we have this cyclic executive is basically what we saw just now, a static scheduling. Everything runs in a continuous loop, all right, in the main. So in this main, what I do is I keep checking for this device A, device B, device C request, and then I finish over here. And inside the interrupt handler, all I do is I do the urgent work, and then I set this. All right, so this is something we have taught you before in APP2. Okay, that in interrupts, okay, you always want to do only what is urgent, what is really critical. Okay, you do not want to hog the CPU inside the interrupt handler. You want to do what is bare minimum, and if you still have further processing to do, you let the main loop handle it. Okay, so you can do that by setting some like flags. Then when the flag is detected to be true in the main loop, then you can carry on to finish up that task. Okay, so this allows us to keep the interrupt handlers very short and very focused on what we need to do. Okay, so the run to completion scheduler, like I said, you can keep sort of a table, okay, to know the information. Okay, this are just some ideas only. You don't need to worry too much about it. But again, this gives you an idea of how the scheduler sort of works. That means what is the information you will look at. Okay, for example, you may look at, okay, how long has it been since I or how frequently must I run this task? Is that a requirement for periodic interval? Okay, and how long was it the last time that I ran this? Okay, and whether I'm ready to run. Okay, so a scheduler, okay, the idea is it actually keeps this information of all the tasks you have. All right, and as and when new information is available, okay, it will update the scheduler sort of list to know which task to go to the ready state and which task to go to the run state and so on. Okay, so the scheduler will help us to manage this. Okay, so in the run to completion model, as we saw, the task is not interleaved. Okay, where you finish up everything that you do. Okay, but you can still have interrupts. Okay, so in this model so far, what we saw is we have 5 tasks, but we never talk about interrupts yet. Right, so the task can still, the system can still have interrupts which may preempt any task at any time. Okay, and priority is generally static, but we will also look at dynamic priority later on. Okay, that means currently I may set the priority to a certain level, maybe medium or high or whatever, and maybe later on I may want to switch it. Okay, so there is also a dynamic priority mechanism that we can use when we are dealing with OS. Okay, in the preemptive scheduler, okay, what we saw, we do not necessarily have to run to completion, all right, and it improves the response time. Okay, so that's the main advantage. Of course, the key thing is the response time may be delayed if interrupts come in as well. Okay, because interrupts can still preempt your task. Okay, so interrupts are the only still mechanism that can have further delay to your response time. Okay, so that, but still a preemptive scheduler gives you that advantage of as close as possible in terms of response. Okay, so the scheduling rules, like I said, this is the idea. So in the preemptive mode, okay, in the preemptive mode just now, okay, so if I come back to the example, if my decode is in the waiting state, okay, and once the data comes in, I transition to the ready state. But when the moment I go to the ready state, okay, But at that time, maybe the record function was running. Okay. And if we look back at our priority table, we can see that decode is considered higher priority, then check is considered second, okay, and then maybe record is third. Okay, so when the scheduler sees that right now decode, which is higher priority, is in the ready queue, that means it is ready to run, okay, but the record function is using the CPU, then it will automatically swap out. So record will go to the ready and decode will go to the run. Okay, so what will happen? The record will go out and decode will come in. So the decode will use the CPU. But at the same time, the table will now be rearranged because decode is already out. So the previously, if you look at the table, okay, this is the top of the table. Previously was decode and maybe check. Correct? Okay, but once decode goes to the running state and record comes back, okay, what will happen? Check will go up and the record will come here. Okay, because now check is higher priority than record. So even though record was swapped out, okay, record was swapped out, okay, it does not necessarily have to go back immediately after decode because the priority of check could be higher than record. Okay, so the scheduler will always keep looking at all the tasks that are ready. Okay, so even though check is ready and record is ready, but if check is higher priority than record, then check will go first. Then the record will go. Okay, so there will always be, or there can always be many tasks in the waiting queue. So there can be a long queue over here. There can also be a long queue over here. Okay, so the transition from waiting to ready and so on and running to waiting, this will happen as and when the code reaches that particular stage and the OS actually helps to look into that. Okay, the transition from the ready to the running is and running to ready and so on depends on the priority of the tasks that are in the ready queue at any point of time. Okay, so all this will become more clearer, okay, when we start with the OS part. Okay, but for now, this is just to give you the idea of what exactly is happening at the back end of a scheduler. Okay, what is the idea behind it? All right, so this brings us again to the whole idea of the module, right, the RTOS. So the idea of the RTOS, okay, in the real time is to make sure that we have the real-time response of any particular requirement. Okay, and as mentioned, the real-time is about fulfilling deadlines. Okay, and the deadline could be anything, can be very fast, can be very long, doesn't matter. As long as you have a deadline and I want to meet the deadline, okay, and I have to meet it, then the RTOS is definitely an important element to consider in your design. Okay, so it of course includes the scheduler, like what we saw just now, plus it includes a lot of other very useful features. Okay, how do I allow inter-process communication? How do I synchronize? Okay, how do I manage my time? Okay, and besides that, how do I do all these other stuff like file system, memory management, and so on? So these are other things we will be looking at, okay, while we are looking at the module. Okay, so in terms of timing, okay, so you can see here in non-preemptive static, basically everybody has the same. So this big over here is to sort of give you the idea that everybody is having the same amount of time. Okay, in terms of the CPU usage, all right, because everybody just goes in a particular order. All right, whereas in the non-preemptive dynamic, okay, you have a particular task that is running, but I can be preempted by other tasks, but I still have each task time to consider as individual. Okay, why? Because when I run to completion, non-preemptive means it's the run to completion. Because when I run to completion, that means each task has its own time. That means even though some other higher priority task comes along, I will still finish up my task first. Okay, then I will go off. So I still have that time for myself. Whereas in the preemptive dynamic, okay, you can see that there is no guaranteed time for any task. Okay, so each task you have written, okay, but at any point of time you can sort of be forced to give up the CPU and another task may take over. Okay, so this is also another important consideration, the memory. Okay, so for the static and non-preemptive, at any point of time, only one task will be running. Okay, so since only one task may be running, okay, you only need to make sure that, so every task will have its own static variables, okay, and its own stack. Okay, static variables are what you declare when you are already running the program. So those are fixed. The amount of memory you need is fixed. Whereas the stack is how much memory you need, okay, as you are running the program. Okay, and this stack size, you will set aside the maximum, okay, based on the one particular task maximum requirement. Okay, and I only need to look at the one task which has the most requirement, because at any point of time only one task will run. Okay, whereas in the preemptive dynamic, okay, I could be running task 2, but before I finish I may be swapped out to task 3, and before I finish I can be swapped out to task 1, and so on. All right, and when I'm swapped out, okay, I will eventually have a chance to come back in and I need to carry on from where I left off. So I need to make sure I have that information in my stack still available. Okay, so the stack requirements will grow, okay, to make sure that I have enough stack for all the different tasks. Okay, so that is why when you're using an OS, when you are creating your own tasks, you will see that every task will actually have its own dedicated stack space, okay, for its own variables and own content. All right, so that will ensure that whenever I have to give up the CPU, okay, my content is still preserved. When I come back, I can carry on. Okay, so the memory requirements will be a lot more, okay, once I go to a OS-based system. Okay, so that brings us to the end of this set of slides. Okay, so let me just do a quick poll of 2 questions. So we talked about foreground background system. So what is the issue with foreground background? So a foreground background is basically what the idea of the main loop and the interrupts. Okay, so this is something you have experienced before. Okay, so what are the issues with such systems? Okay, some tasks will be left off. Have to wait for an entire cycle before running a subtask again. Not efficient. Cannot prioritize tasks, long delay. Not very efficient. Requires more memory. Okay, so the foreground background system is what we have been using so far, the main and the interrupts. So in the main and the interrupt, basically what happens, as we know, your main program runs some loop, okay, generally in fixed sort of sequence, and then you have interrupts to trigger events. Okay, so some tasks may be left out. Okay, as long as you put it in the sequence in your main loop, there's a chance that it should get executed while you're going through the main loop. Okay, yes, you have to wait the entire cycle before running a subtask again. Correct. So if you don't put a particular task in the interrupt, you have to go through the loop complete before the next time you get to run it. Okay, it requires more memory. Okay, the memory usage in this case would be more or less quite consistent, because Your main loop, you already write your code, you already know how much data you want or how much memory you need, plus your interrupts. Again, interrupts usually you don't declare new memory in the interrupt. You use your global variables or your currently available variables to store information. Okay, so the memory usage may not increase so much because of foreground or background system. Okay, so one of the things, okay, the task cannot be prioritized. Okay, so a task cannot be prioritized is true, but you have the ability to prioritize interrupts. Correct. So the task, yes, is still going in a sequence, but you still have the option of prioritizing interrupts. So in that sense, you have some level of handling events, okay, but still the tasks are going in a sequence. Yeah, so you still have to wait. Okay, so one of the things, okay, but I think no one mentioned that is your response, your real-time response is sort of limited to what is available in terms of the hardware. Okay, that means if I want to use interrupts to capture certain events, I'm limited by what the hardware is able to offer me. Okay, so that is one thing. All right, and of course, another thing with foreground, background system with interrupts, you also need to be careful is if you have interrupts that happen too frequently, okay, then you can also hog the system. Okay, that means you have an interrupt that keeps happening maybe every few milliseconds, and then every time you keep jumping to the interrupt, and what will happen is your main loop gets significantly delayed. Your other tasks may also get delayed, your other interrupts. Okay, so you also need to be careful of making sure that your interrupts, how do you manage them, okay, in a way that they do not hog the whole CPU due to over usage. Okay, so this is so when you have many interrupts, what your potential issue? I think I actually just talked about this. Okay, so it is basically to look into the issue of okay, so one thing that I mentioned just now is the ability of or the issue of one particular peripheral or subsystem hogging the whole CPU. Okay, but what other issues could there be? Okay, insufficient memory on the stack, lower speed of system. Slows down other tasks. Okay, so defeats the purpose of interrupt. It takes up a lot of operating time. Okay, that could be an issue. Main body cannot run, correct? So yes, okay, so these are all potential issues, correct? That means you have many interrupts happening, and then your main loop cannot run, okay, and then your main loop gets delayed a lot. Okay, so another potential issue is also when you have the situation where different peripherals may generate interrupt at the same time, then do you allow nested interrupts or you disable nested interrupts? Okay, so these are also factors to consider. All right, I think we talked about nested interrupts before in EPP2, okay, where you can have an interrupt being interrupted by another peripheral of higher priority. Okay, so these are again usually configurable. It's whether you want to allow it or not allow it, okay, in the system. Okay, so as you can see, interrupts based foreground background system is very useful. but it also comes with its own share of challenges. All right, but having said that, like I said before, it is also a very, very good approach that can help you solve many problems. All right, only when you feel that your complexity of the system is going up, the real-time requirements is more, all right, or more important, then the software-based RTOS approach is going to be very helpful. Okay, so that is what we are going to be focused on, okay, in this module. Okay, so thank you for your responses. Okay, so let me, before we go for a break, just a few things. So what's happening this Friday? So let me just remind you, this Friday is your lab, but it is not, there is no attendance or anything. Okay, but you need to drop by to collect your freedom board. Okay, so in the lab one manual, I listed out all the steps. Okay, later at the end of the lesson today, I will show you a short demo on what you expected to see. Okay, once you run through the code. Okay, so this Friday you're supposed to go to the lab to collect the board and test it out. Okay, and make sure everything is okay, and make sure your software is already installed before that. And if you have any issues with the software or the board, the TAs will be there to help you. Okay, so you don't need to do any soldering this week. Okay, you just need to collect the board. Okay, the rest of the stuff, the TAs will probably be packing on Friday itself. So if you are coming in a bit later, maybe you should be able to collect it. Okay, but the collection of project kit items is only for those who already registered the team. Okay, if not, you can collect it next week. Okay, but you do not need to rush to that, because this lab and the next week's lab is just the board alone. You don't need to do soldering also. Okay, it's just the board alone only, just to get the, making sure everything is working well. Okay, so usually at the end of most of our lectures, I will do a demo so that you know what to expect in the lab and what you're going to be doing. Okay, and because of this demo, usually what happens is the time is maxed out. That means though the class is like 9 to 11 and we're supposed to end earlier, but I will usually go all the way until 11 because I'm doing this demo. Okay, so if you cannot stay till the end because you have another class to go to, then it's okay if you drop off, but try to look at the recording later on to catch up and see the demo, so you roughly know what you're going to be doing for the lab. Okay, for this Friday, if you are not going to come to the lab, you need to, it's fine, you can get your friend to collect for you. Okay, but you need to tell your friend, and your friend will sign on your behalf as well. Okay, for the collection. Okay, and if you have not been to the campus yet, please remember that you need to go collect your self-test kit. Okay, and do your own swab test. Okay, and upload the picture. All right, so if you're not collected, when you come to the campus, okay, then you can collect and do it. Okay, so Fridays is usually quite relaxed because nobody uses the DSA lab already, so you can use the lab, all right, and settle it before you leave. Okay, so we will go for a short break now. Okay, and then we'll come back and we will start with the next chapter. Okay, and then after that, I will go through the demo so you understand what you're going to be doing for next week. I mean, this Friday's lab. Okay, if you have any questions, you can just put in the chat here. Okay, later when we come back from the break, I will address your questions. Okay, thank you. I'll see you in a while. We'll go for a 10 minutes break. Now it's 10, so 10:10 we'll come back here. Okay, so welcome back. Okay, let's continue. Okay, so in our Luminous, okay, under the lab material, okay, you should be able to see two documents there under microcontroller documentation. Okay, so these are the two data sheets that you need, okay, to download and keep with you. The first one over here, the KL25, that is the full reference manual that goes into very clear, in-depth details of all the whole controller architecture. Okay, so we will be covering part of it. Okay, and we will be learning how to extract important information from the data sheet to help us with the understanding. Okay, and this is something that I also want to sort of make sure that you all get the idea of it, how to effectively do it, because when you given any new controller, any new subsystem or peripheral, the only thing that you have to refer to as a good resource is generally the data sheet. Okay, so the data sheet always gives you good information on how the controller or the board works, okay, what to do and so on. Okay, so this is of course focusing on the microcontroller. For the KL25Z board itself, is another document. Okay, this one gives you just a brief overview on the board itself, what are the features and so on. So we will come back to reference this material, okay, as we go along. Okay, and that will give you confidence in doing this on your own later on. Okay, how do I learn something just by looking at the data sheet and looking at the information given? All right. So let's continue first with our lecture slide. Okay, so now we are in lecture 3. Okay, so we're going to start off by first understanding the core, okay, the CPU core, and trying to appreciate what we are having here. Okay. Okay, so can everybody see the screen? Yes. Okay, thank you. Okay, so just one more thing. Yeah, I mean, now we have about 63 participants. Okay, so about 30 students or so did not turn up. All right, they are probably going to watch the recording, I hope. Okay, as much as possible, try to attend the live lecture. Okay, I think it's more beneficial because it also gives you sufficient information to prepare you for the week's labs and tutorials and so on. Okay, of course, the recordings are there. Okay, but usually with recordings, what happens is a 2-hour lecture will become a 4-hour lecture when you record, when you want to see it, correct? Now, when you sit down to watch, and then your friend will message you that the latest Korean drama just released on Netflix, you have to close me and go and watch the Korean drama. Then by the time you come back, it's 2 hours later, and then you're tired. Okay, so a 2-hour lecture will become a 4-hour lecture or a 6-hour lecture. Okay, so try to attend the class, so at least for that 2 hours you know what is going on and then you're prepared for the lab. Okay, so we're going to get to know the CPU core first, okay, the Cortex M0 plus, and then the subsequent few lectures are all going to focus on the peripheral subsystems. Okay, and each subsystem we are learning is actually helping us develop some part of the project. Okay, and it will help you, right, so that you will actually are working on the project while you are doing the labs. All right, so this is before we go there, let me just ask you this simple question, and I'll explain to you why later. Okay, so this is something we do every day, correct? Okay, at some point of time in the morning, in the night, whatever, we will see that our battery is low, we will charge our phone. Okay, now my question to you is, if you do this right now or later and you see that your phone is not charging, okay, when your phone is not charging, you do what you do every day, but suddenly today when you do it, your phone is not charging. My question to you is, what do you do? Just tell me naturally, what will you do if your phone is not charging? Okay, unplug, try again, another charger, restart, check the power, get a new phone. I want to be your friend. Okay, go different plug point, pray to God. Okay, cry. Okay, so generally, I think most of you get the idea, correct? That if you expect it to work in a certain way, but it doesn't work, you go through this process of troubleshooting. All right, and that is the same mindset you must have when you're doing this module. Okay, why? Because I've Then sometimes when I come and walk around the lab, and the students will tell me, oh, I download the code that you gave, we run everything, but the motor is not running. Then I say, okay, the motor is not turning. So what have you done to check? They said, nothing, I just run your code, do the hardware by now. So what did you do to check? And then they look at me like talking in other language, correct? So if things don't work, you must have a plan of trying to figure out what is the issue, right? So of course, the first thing, the easier thing to check is generally the common things, correct? Like maybe the power supply, did you switch on the board, okay? And some, so there's two aspects. One is the software side, one is the hardware side. So when you are checking the hardware, you check whether the power is there, the hardware connections are correct, okay, everything is there. Then at the software side, you check whether, even though you follow the code given, but maybe you missed out on some earlier definitions or some header file you missed or something, all right, that you maybe copied wrongly. Okay, so there could be many reasons, correct? So you need to check from the software side, check from the hardware side. Okay, if you can't see it, then ask one of your teammates to look at it. All right, then if of course everything is correct, then you say the motor is not running, then you need to go deeper. All right, then you may need to use a multimeter, use the scope, check whether the signal is coming out correctly. Where is the fault? Is it the microcontroller at fault? Is it the motor driver at fault? Okay, so you need to go through this process of troubleshooting and trying to figure out what went wrong. Okay, because if you just call the TA and then you say that it's not working, this is probably what the TA is also going to ask you. All right, what have you checked? Okay, have you checked the software? Have you checked the hardware? Have you checked this? Have you checked that? So you should make it a point to do this first level of troubleshooting on your own and try to see what could be the issue, so that when you call the TA, it is more it is a lot more beneficial. Correct? That means you can already tell him that, okay, I did this, but it did not work, so I'm not sure what is the issue. All right, then we can look at other angles. Okay, so this is important. All right, you must have this mindset. Okay, especially as computer engineers, hardware and software both are involved. So you need to troubleshoot and look at it from both angles to see what could be the issue. Okay, and sometimes if you cannot figure out the issue, then you need to go back and look at the signals, whether the signals are coming out correctly and so on. Okay, so that is how you must train yourself in this module to make sure everything works. Okay. Okay, so that is to again prepare you with the correct mindset when you start with the lab work. Okay, Cortex M0 Plus core register. Okay, so that is what we're going to go through, some memory addressing, instruction set, and so on. Okay, so this is not a module that is going to teach you ARM assembly language. Okay, there is already another module where you are learning about the ARM. I think it's 3720 or something like that. Okay, or 3700. Okay, can't remember the module. But there is, I think, one or two modules where you will learn about the ARM architecture and as well as some ARM assembly language programming. Okay, so over here, what we are going to be focusing on is getting a bit of understanding of the actual microcontroller and the microprocessor we are dealing with. All right, so that we appreciate what we have. So the whole microcontroller, like we discussed, is the processor core, which is this, all right, integrated with all your other subsystems. Okay, your memory, your clock, your analog, your timers, and so on. So everything put together in that single chip is the KL25Z chip. Okay, but the main processor core is the Cortex M0 Plus. So if you look inside the Cortex M0 Plus, internally it has all these components. Okay, so this is the core of it. Okay, the NVIC is the interrupt controller, which we'll be looking at I think the next lecture or so. So that is to manage interrupts. Okay, so you can have interrupts coming in from many different sources. So the NVIC helps us, or help the processor to prioritize and send these interrupt signals to the processor core. Okay, and then you also have debugging hardware. Okay, so these are all part of the whole main processor's components. Okay, in terms of architecture and memory speed, Okay, so this is basically, okay, so all processors have a bunch of registers. All right, so this ARM is considered a RISC system. I'm sure you all know what is RISC. Does anybody want to share? What do you think is RISC? You can put in the chat. Anybody? Yeah, so it is reduced instruction set computer, correct? Okay, so reduced instruction set. Okay, so the other side to it is the CIS, complex instruction set computer. Okay, and the main difference is the type of instructions that you have. Okay, in the RISC architecture, you have instructions that are focused on a particular task at any time. So, for example, add. Okay, so if I say, for example, add R0, R1, R2. Okay, so you will do an add between R0, R1 and put into R2, R1, R2 and put into R0. Okay, so it will be a very simple instruction that is focused on a particular task. Okay, so it's a very reduced instruction set, whereas a complex instruction set is where the instructions can be highly complex. That means in one instruction, you can specify a lot of things to do. Let me take two sets of data, do an addition, then later do something, do a shift, and do this and do that. All right, before you store the result. All right, so there are basically two different sort of architectures, and ARM has always been a RISC-based system. Okay, so in order to, so one of the things about ARM is also it's a lot of registers where data data is stored. Okay, I mean, when you do assembly language, basically you are dealing at the processor hardware level. Okay, so even though when we write in C, when you compile the code and you get translated to assembly, everything is dealing with registers and dealing with this kind of assembly language instruction. Okay, so when you are doing that module on assembly language, okay, then you will write instructions that deal directly with the hardware. Okay, when you are dealing it at a higher level, like right now, you let the compiler do this for us. Okay, so in any RISC-based system, basically what happens is you generally take the data, put it into register. So R0, R1, in this case R1, R2 could refer to variables X and Y. All right. So X and Y, where X and Y are somewhere in your memory. Okay, so if I look at my memory, so maybe X is over here and Y is over here. So in my C code, I might say Z equals to X plus Y. Okay, I want to do this. I write this in C. Okay, but when I compile, what happens? Okay, X is some memory, Y is some memory, and I want to do an addition, but I cannot do operations on memory. Okay, all operations have to be done within the registers only. So prior to doing this add operation, I need to have a load. I need to do two loads. Okay, so the actual syntax again depends on the processor you're dealing with, but generally what you want is take the content of the memory location in X and put it into R1. Okay, and Y, take the data in Y and put it into R2. So that's why the first step here, you load the data from memory into my internal registers. Okay, then I perform the operation, which is this. I do the add operation. So after I do the add, I have the result in R0. So maybe Z is over here. And I want to store back into Z. So after everything is done, I need to do a store. Okay, which is R0 into wherever Z is. So I'm just trying to give you a pseudocode only. This is not the actual ARM syntax. Okay, but the general idea is this: you load the data from memory, okay, you process it, and once you are done, you store it back into memory. Okay, so that is the load store architecture of that is followed in the ARM core. So these are the ARM processor registers. Okay, so you have R0 to R12. Okay, plus you have a stack pointer R13, link register, program counter, and some special registers for status. Okay, again, all these how to use them for programming is another module itself. Okay, but here I just give you some overview only. All right. And this is the question that I asked last week. When we say it's a 32-bit core, what is 32-bit? Okay, so when you say it is a 32-bit processor, that means it can handle 32 bits of data at any point of time. So to handle 32 bits of data, that means all my internal registers should also be 32 bits. Okay, so all our registers that we see here, R0 to R12, SP, everything, they are all 32 bits. So at any point of time, I can take in 32 bits of data, okay, in two different registers and do some processing with it. Okay, so that is the idea of saying that it's a 32-bit processor architecture. Okay, stack pointer is basically a pointer that points to a stack which is a memory set aside, okay, to hold some data for us. Alright, so in here we have two stack pointers, main and process. A link register is used to hold the return address. So whenever you jump to a function, okay, you need to jump back to the correct address after you return from the function. Okay, or you complete the function. So the link register is to hold the return address for us. Okay, and program counter is just basically to point to the address of the next instruction we are going to execute. Okay, so in terms of operating mode, okay, whenever we come out of reset, we are in what we call the thread mode of operation. Okay, this is the default mode of the processor, and we use the main stack pointer. Okay, if we are going to handler mode, okay, the handler mode is basically the interrupt mode. Okay, so whenever there is a handler or sort of interrupt request that is being serviced, okay, then we will go to this handler mode. Okay, and then when it's finished, we'll go back to the thread mode. Okay, so that is the two modes of operation of the processor. Okay, in terms of the status registers, these are some of the status registers we have. So we have the APSR, application program status register. Okay, so this one, you will basically have 4 flags over here to tell us whether it's negative, 0, carry, and overflow. Okay, these are again used extensively when you are doing assembly language programming, but for us, we won't need to look into it. The IPSR is important because it tells us the exception number we are dealing with. So later on, when we're talking about interrupts, we will want to know which interrupt we are dealing with. Okay, so the interrupt program status register helps us to give us that information. The EPSR is not needed now. That is to operate in thumb mode, okay, or ARM mode. Okay, so what is thumb mode or thumb state? Okay, so so ARM is generally, we say in ARM state, we call it the 32-bit. Okay, so of course your whole ARM is 32-bit. Then they decided to just take one part of the ARM, which is your thumb, and that is called 16-bit mode. All right. So this thumb mode was brought about because of a need for some developers who wanted 16-bit architectures, but they still wanted to use ARM. You know, so the thumb state came about as a nice in between where you have the ability to still use ARM processor, but you use them in 16-bit mode. Okay, so but again, that is for assembly language programming. We will not go into that. Okay, so this exception mask register and control register, okay, I will not go into this so much. Okay, all this is just to give you the idea. All right, but the exception mask register is used, okay, when you want to mask an exception. All right, so if I do not want to have exceptions, so exceptions, the same idea. exception is similar to interrupt. So when you say I have an exception, it is the same as having an interrupt. The only difference is because we are used to having this term interrupt for many of our peripherals, correct? GPIO interrupt, PWM interrupt, UART interrupt. All right. So generally we say the interrupt or the concept of interrupt that we know is tied to peripherals or tied to events which we want to happen. Exception is more of a higher level term that covers interrupts plus other events that may not necessarily be what you expect to happen. Okay, so it could be even cases where there is some fault, memory fault, segmentation fault, and so on. Okay, so exception mask register allows you to, it's just a general name. Okay, it also covers interrupts. So if you want to mask interrupts, you can use this prime mask register. Okay, to decide whether you want to allow exceptions or you want to block all exceptions. And you block all interrupts. Okay, this control register. Okay, you have the stack pointer selector. Again, you will not touch all of this. All right, you will leave them as they are in default mode. Okay, whether you want to go to privileged or unprivileged mode. Okay, as well as PSP and so on. Okay, so this privileged or unprivileged mode is something interesting, where it means is that you can allow the code or some mode of operation where you have privileged access or unprivileged access. So when you say you have privileged access, means your software is able to do anything to the hardware. Okay, if I say unprivileged, okay, that means you are allowed to do certain things, but certain things are not allowed. Okay, so one good example you can think of is the mode of operation of, let's say, an app running on your phone. Okay, the OS that runs on your phone has to have privileged access, correct? Because it must be able to do anything. All right, but the app that runs on it, you will want to give some restrictions, correct? Or the OS itself may want to impose some restrictions that it cannot try to mess with certain peripherals or certain memory regions because those are reserved for the OS. So you cannot allow access to that. So your app that is running on your phone is generally in unprivileged mode because it cannot just try to take over your phone. All right, certain things are blocked. So that is where the privileged, unprivileged sort of mode comes in. Okay, this is the memory map. Okay, so the memory map, we will go through more detail later on. Okay, but the memory map of a system gives us the full snapshot of how it is, how the entire memory space is used. Okay, by the sort of hardware that you have. Okay, so this memory map, okay, I think last week when we were talking about 32-bit, some of you were asking about the address range and the data range and so on. Okay, so this memory map of any processor is tied to how much, how big is the address bus that it has. Okay, how big is the address bus that it has? So if you look over here, okay, this is the address range, okay, of the entire processor. Is 0000 to FFFF over here. So this is the full address range that your processor is able to access. Okay, so what does that mean? Okay, what does that mean? If you say that, okay, I like this Cortex M0 Plus, but I don't want the KL25Z, I want to create my own processor. That means I want to integrate my own memory, my own peripherals, everything, and create my own microcontroller, but using this Cortex M0 Plus. Yes, you can do that. Okay, so how do you do that? You now need to come back to this memory map and create your own memory map. Okay, so in this memory map, they have already set aside, okay, that, okay, the first 128 kilobyte of flash maps to starting from address 0 up to this address. So this is 128K kilobyte. Okay, so that is for the code. Then subsequently, they have set aside, okay, for example, different memory regions for all the RAM and so on. But these are all things that you can decide if you are going to build your own processor. Okay, similarly, over here, if you look at peripheral, okay, when we are starting the peripheral subsystem next week, okay, you will see that most of the addresses start from this 0x4 something something. Okay, it is not has to be that. Okay, it is just that the way the controller was already designed, that the peripheral blocks are all mapped to this address. Okay, so since they're all mapped to this address, all the registers associated with the peripheral subsystems, we will be using this. Okay, and over here, they've also set aside, again, all these memory regions for different purposes. Okay, so this space is your own free space, this entire space. Okay, this entire space over here is for you to decide how you want to map different parts of the system if you're building your own, okay, own microcontroller. Of course, there can be some restrictions. Okay, generally, most controllers have reset vector at 0, so you probably want to have your flash at that location. Okay, but subsequently, the rest of that space is free for you to decide where you want to map them to. Okay, so that is the idea of the memory map. So in this case, or in this module, since we're using the KL25Z, we will follow the memory map given to us. Okay, the next one is the Indianness. Okay, so what is Indianness of a system? Okay, so there is two ways in which data can be stored. One is little Indian or big Indian. And what does that mean? Okay, so if I give you a data, okay, in hexadecimal, I give you 1, 1, 2, 2, 3, 3, and 4, 4. Okay, and this is a 32-bit data. Okay, 32-bit data. And if I say I want to store this 32-bit data, that means 4 bytes of data in my memory. Okay, so a multi-byte value is stored in memory in single bytes, correct? So how do I store it? So there's two ways in which I can store it. Okay, there's two ways in which I can store it. So if I look at it, okay, from the address, okay, let's say I break it up. Okay, this is 0x. Okay, let's say this is A0, this is 0xA1, 0xA2, 0xA3. That means these are 4 address locations, 4 bytes, starting from A0. So A0, A1, A2, A3. Okay, and this is the least significant byte, and this is the most significant byte. If the least significant byte goes to the lower address, okay, so if the least significant byte, okay, 0x44 goes to the lower address, okay, that means the order will be like this. Okay, the least significant byte 44 goes to the lowest address, and then I go up. Okay, so this will be what we call the little Indian. Okay, the other option is the big Indian, where the least significant byte goes to the highest address. Okay, now why is this sort of important? Because in your code, okay, generally when you write in C, we like to deal with pointers. Okay, so when you try to deal with pointers, in many cases, your multi-byte data may be organized in a way that different bytes represent different things or different pieces of information. Okay, so you may want to access a particular byte offset from a memory location. So you may need to know exactly which address you are referring to. Okay, that is of course if you are doing it at the address level. Okay, so whenever you're dealing with addresses, okay, you're trying to access information using the actual address of the memory, then of course whether it's little Indian or big Indian is important, okay, for us to know. Okay, but if you're not doing that, then generally it is fine if you don't quite know how it is stored. Okay, but again, the idea of little Indian and big Indian is important. So you know that multi-byte data can be stored on a computing platform in different order. Okay, so in EPP2 also we looked at this, correct, where if you have different systems with different order and they try to communicate with each other, then that can also be a problem. Correct? When you try to serialize the data and you send across, the order of data that you get from one system to another system may be in the reverse. Okay, so you need to be aware of how data is managed in each system when you have sort of different systems talking to each other. Okay, so in our case, ARM follows the little Indian in this particular ARM v6 architecture. So everything is little Indian. All right, so that is how transparent to us. Okay, so this is what I was mentioning just now, the thumb and thumb2 instructions. Okay, so ARM and thumb. So ARM is 32-bit. Okay, this is 32-bit. Then later came out with 16-bit. Okay, to support some industry requirements. Okay, and then they sort of realized that they needed to support both at the same time. So they came up with this new architecture or instruction set, which is thumb2, which allows sort of intermingling between 32-bit instruction and 60-bit instruction. Okay, again, these are things that you will probably look into more detail when you're doing the assembly language course. Okay, for now, just take it as information only. All right, so again, I will not go into all of this. Okay, all this is just for information to understand what is happening. But effectively, since we are dealing with C, you don't need to worry about this so much now. Okay, so just one more thing before I show you the demo. So as I mentioned, once you collect the board, if you can, you should try to do some 3D print for casing. Okay, if not, it's also fine, but do take good care of the board, all right, because it is quite sensitive, like I said. Okay, so before we end, I will show you the demo, okay, on what you're going to be covering for this week. Okay, so this is your lab 1 manual, all right, where you'll be getting your freedom board. Okay, so when you first collect the freedom board, okay, so let me show you the board over here as well. Okay, so when you first collect your board, then you first collect your board and you plug it in. Okay, you will see that it will actually sort of show up as sort of a USB drive, okay, on your computer, and by default there is already a code loaded onto it. Okay, and that code, what it does is it will actually if you tilt, I mean, if you take your board and you tilt it like this way and so on, you will see that the RGB LED changes color. Okay, because there is an accelerometer already built in to the board. Okay, and the default code, what it does is it sort of uses that information to adjust the RGB LED on the board. Okay, so that is what is the default code, right? And you will see, and in that mode, okay, that means in the default mode of it being a thumb drive, okay, again, why it was in that mode is, I think one of the main reasons is they wanted to promote the Embed OS platform. So in the Embed OS, when you build your code, okay, it generates a binary file which you just drag and drop to the board, okay, and then it will start to run. Okay, but in our case, we are going to be using the Kale software, right, because of all the low-level hardware that we are going to be developing. So you need to follow the steps to install all these drivers. Okay, the software is also uploaded on Luminous. So you just follow the instructions to upload, to install your software. So all this, you should probably do it before you come. Okay, and then there's a sample code called the RTX Blinky. Okay, and what you need to do is once you open up the code, there is this one step that you need to program the KL25Z port with a new S19 file. Okay, so the purpose of this is to make sure that the board comes out of this flash drive mode into USB debug mode. Okay, once you come out of the flash drive into this USB debug mode, then you can use the KL software to do the coding. All right, so to test that part, okay, is where you're also going to be doing this. Okay, where you're going to be programming or running a simple sample program to make sure it can blink the LEDs. Okay, so let me just show it to you over here. So this is the KL software. Okay, so once you follow the instructions, you'll be able to. So this is a sample code that is given. All right, when you open up your project, okay, you can see the code, everything, but don't need to worry about the code for this week's lab. Okay, so in the example, basically what you're going to do is, okay, so let me put it here. Okay, you're going to build the code. Okay, once you have built, you can go to debug and you can say start. So you'll see that over here, you will start to debug the code. Okay, and you'll start to connect. So once it's connected, okay, you will switch the display to the debug mode display. Okay, so you will explore this along the way, don't worry. Okay, and this is where you can actually also see the assembly language code interlinked or interleaved with the C code. Okay, so here you can see that the C code and the associated assembly language code will also be available. So this gives you the idea of how assembly language is sort of written for the ARM core over here. Okay, but we're not going to look into the code or anything now. Okay, so this is the actual C code, blinky.c. All right, all you need to do is you just need to click on the run button over here. So when you click on the run, okay, you should observe that the RGB LED goes blinking in sequence. Okay, once you see this means it is fine. That means your whole software, your hardware, everything is set up correctly. Okay, there shouldn't be any issue after this. Okay, so this is the only thing you need to do for this week's lab. Just go through the lab manual, make sure that you follow the steps to install the software correctly. All right, install all your driver, and then subsequently you can make sure this RGB LED is blinking with this sample code. Okay, so you don't need to do any soldering, no need to write any code. Just check that this is fine. Once you see that this is working for your board, all right, then you should be good to go. You can leave already. Okay, you don't need to stay for the whole session. Okay, so that is the objective of this week's lab. Okay, just to come and collect the board and make sure everything is working. All right, the rest of the stuff, okay, I cannot say yet because the TAs will only be packing this Friday. So if it is done, you might collect it. If not, you just have to collect it next week. Okay, but it is fine. All right, next week's lab, all right, you'll be on the, again, RGB LED, but writing our own code for it. So you still don't need to rush to collect the components or even do soldering yet. Okay, next week's lab is still just based on the board. The following week after that will be where you need the connector pins and so on. Okay, so that is the objective for this week's lab. All right, so let me just again show you the registration. So under the module, if you go under class and groups, okay, under class groups, okay, I've created 2 folders. So depending on which project group you're under, BO1, 8 to 10, or BO2, 10 to 12, okay, please select that particular one and you can enroll under any team. So that the team number doesn't matter. Okay, so you can choose any team number, just click on it and enroll yourself and ask your teammates to also enroll themselves inside. Okay, so like I said, maximum is 4. Okay, and you should have at least 3. Okay, those of you who have only 2, okay, I will If you don't have anybody else, then in the end, when we have students who do not have a team, okay, then I will assign them to those teams. All right, so every team should have minimum 3 students. Okay, so those of you who cannot form a team yet, don't worry. Like I said, I will collect your names and then I will do the manual allocation later on. Okay, so that's all I have for today. So next, this Friday, please remember to come to the lab. If you're not coming, then ask somebody to collect for you on your behalf. All right, then we will just record that down. Okay, there's a question on seating arrangement. Okay, so for this Friday, there is no particular seating arrangement. Okay, you can just come and you once your board is settled, you can leave. Okay, so the seating arrangement I will finalize once all the team registrations have been in place. Okay, so that's all I have. Any questions you can ask me. All right, if not, thank you very much, and I will see you all for the next lesson.